floor is yours.
Okay, so first, thanks a lot for our speaker, and now it's panel discussion. So just in case maybe some audience just be new here. So we have Eric from NVIDIA, we have Yingzhu from Columbia University, and also we have the Felix from the Stanford University. So my job is just to warm start the panel discussion, and like the organizer mentioned, it actually really encourage you to ask more questions and also to have more in-depth communication with both our very nice panel speakers. So first, I think warm start question is like, so recently we saw maybe many different simulations in this community. Some are maybe based on analytic ways, some are based on maybe network way. So general question is like how to define what is a good differentiable simulation, and especially based on our context of this conference, maybe for robotic application. So what's your opinion for what is a good differentiable simulation? Yeah.
Yeah, so I mean, in my opinion, it should be something that's generalizable, something that can also leverage existing information you have potentially. Like we have maybe some existing CAD models when we are in indoor environments. So I think we should be able to reuse some of the knowledge we have. And that also pertains, I think, to parameters, where we have a good understanding from the design of the robots, like what are the inertial properties and the like material properties. I mean, it's not all completely up for grabs, like what could be learned, I think. So as much as possible should be, I think, leverages pre-existing information. And then on the other hand, I think there should be also something that makes it easy to optimize. So, and I think that's the challenge with these conventional, even differentiable simulators, that you actually get gradients, but they're not really that useful sometimes for control. But I think coming up with some ways to make it more useful for control is also important. Yeah, I think that's the biggest lagging point probably.
Yeah, I totally agree. So I'm a very practical person. I work on robotics. I just want to see whether those simulations is useful for my robotic applications. So my lab have been trying actually a number of like differentiable simulations, and we found two pain points. The first one is how easy it is to actually instantiate the real world environment into your simulations. Sometimes it can be very tricky because the real world is partially observable, and if somehow you like there because of like perception noise, there could be some perfectly match the real world. It doesn't have to be, but it has. Like you said, like how useful the gradients are. Sometimes the gradients are actually very local. And we find something actually quite interesting is that typically the more detailed and more accurate your simulation is, the less useful the gradient is. I can take a very like classic examples from like differentiable rendering. Like I remember the work from like Fredo's lab at MIT. They built this differentiable renderers. And they are doing some very simple like inverse estimations using the gradients from this differentiable renderer in trying to estimate the camera pose. But even if the camera is certain distance away from the targets, they have actually to like apply some low pass filters to blur the image to make the gradients more smooth. You want to do the optimizations. And as they're getting closer and closer to the target, they are using higher and higher resolutions of image. It actually makes me feel like the gradients may not be that useful, and how to do effective optimizations with the gradient from the differentiable simulators. I think that's the second major pain point.
So what's really important is that we have a high level of smoothness. That's kind of what we also pointed at. Always the question is how valuable are our gradients? How much do they align with the direction that we actually want to go to? Often it's not about actually computing the exact gradients of whatever our simulation is, but rather just getting the right direction to optimize to. And when we impose higher levels of smoothness, we actually tend to get better directions.
Great. Thanks again, audience. If you have any question, yeah.
This is for you. So this goes into sort of what you were showing with all your you know, a lot of these tables. What I want to know is how did you integrate the fact that, or if your method doesn't already, the fact that you have a tabletop. You said it was 3D, but you also have to assume that there's like a consequence there. So somewhere you bake this in there, or your model's naturally about this. How would you then go about extending that to a scenario where you have more complicated interactions with the environment? How do you select the right one, right? Versus only like a table. And maybe it's supposed to everybody. Like, how do you select the right interaction you care about?
Yeah, that's very good questions. So you're right. Many of the tasks we've been doing are only constrained in a tabletop environment, which like we already find there's a lot of very interesting problems and questions you can answer just within this tabletop environment. But obviously, we're not satisfied with that. We want to extend to like larger scale environment in the kitchen environment, in the living room environment. So that's why currently we are working on the directions that combine mapping with graph-based neural dynamics models. Meaning that you are not just like instantial graph in front of on the tables in front of you. You're combining SLAM with graph-based neural dynamics models to really extend the scales of the framework into a larger scale in the room scale, or even, for example, in the wilds. We actually have some very recent investigations and trying to do mappings over like a granular terrain instead of just like a few granular pieces on the tables. So, but yeah, we'll see how far we can go about that.
But in your existing work, do you just assume you just know it's on the tabletop to constrain your problem? But even a slope would mess you up a little bit, right? Like if you said, oh, it's on strings to the XY plane, but you were on the slope.
So first, we didn't consider slope. So if we encounter like a large slope, it will fail. And so the how the model internalizes the location of the table is by either one, we have some particles on the table. Such particles representing the collision geometry. It's like we use particle to represent the geometries of those tools. The second is that there can be some bias terms in the neural network that just fix the objects there. Yeah.
To me, there seems to be some gap between the classical approach where we analyze these simulations classically and the neural network approach. So if I give an example of two soft bodies colliding, right, and in this case, you might have a model for the encoder for all the particle interactions within the first soft body and the second soft body, but not between them. So how does the graph neural network approach actually deal with this type of novel interactions? If we go into the classical approach, we definitely, as long as we know the models of each of them, we can simulate it perfectly, but it can be very, very expensive to do cross simulations classically. Right? So there seems to be this gap between the RL approach and the classical approach there. What's the current stance on how we tackle this type of issues?
Maybe a little bit is more like for data-driven method and also fake-based method producing from trade-off or even maybe future combined together.
And I think also on the topic of class simulation, that there's actually, I think, computationally, it's very similar, I think, actually, to the graph-based particle approach, actually, because the kernel still operates on these graphs, so like a mesh, basically. I think computationally, it's very similar. So I'm not sure that would be maybe something for learning-based models to improve on. It's just, I think the gradients are probably better behaved, maybe to infer some properties. And I think they can probably capture more behaviors than what a class simulator could give you, that only can do whatever per element or elasticities or whatever can be done in class simulator can learn.
So regarding the gradient quality, one thing that's very important is that the forward and the backward, that they match each other, so that we are computing the gradient of the actual function that we're doing in the forward. As soon as we have some mismatching there, we often get worse performance. This, of course, very much depends on the particular simulation. But in general, it is beneficial to have a forward that corresponds to the respective backward. Now, if we introduce some smoothness properties to get a better gradient quality, we can't just change the fake or make a fake gradient that has higher smoothness properties, but instead, often better to take the forward and make it such that it has better differentiability properties, such that we have the natural gradients, that is the mathematically defined gradients of the forward being the backward and using them in optimization.
So first, to answer your question, so if there are some kind of novel interactions that the model has never seen before, it will fail. So typically what we do is that we at least have data that contains, for example, 2 objects interactions. And then you'll be able to generate to like multi-object interactions. You may have new objects, but it's still like same type of interactions. So they can still give you certain levels of generalization capabilities. And more broadly, to answer the question, is that if you think about learning-based methods or physics-based methods, it's still a function. It's just a function class are different. And the number of parameters in that function class you have to do the estimations for are different. A lot of the underlying principles are actually very similar. For example, how you represent the environments, like how to instantiate the connectivity structures between those things are actually very similar. It's just like I have a firm belief that this graph-based neurodynamics model can be scaled up and benefited from the reason trained on large-scale data collections. Like I said, like some interactions you may have never seen, but with a vast amount of data, you probably have seen a lot of like type of interactions that can even generalize to some slightly different but novel type of interactions. So with more like generalizable and scalable structures, I believe like we'll be able to like push this further. So far, I cannot predict what will happen, but we are very like committed in scale it up and see what happens.
I have a question on the actual like choice of contact model. So a lot of the choice of contact models would effectively change the way that like the gradients are taken. So my question is there a right contact model as a means to sort of replicate real world examples, or is that sort of barking up the tree?
Yeah, I think it's super hard to come up with a good contact model. Maybe Justin has an answer for that. But I think what I found so far is that the soft contact models work pretty well. Like in what I showed with the FEM, the bear, that was just these 20,000 tetrahedrons, and getting those activated in the right way actually yielded a good walking behavior in the end. So I think surprisingly, the softer the whole model becomes, the better it is. I think that's also what Felix mentioned. I think this translates to the contact model, it seems. Maybe if you have multi-contact problems and you still want hard contacts, there might be some way to get a bit more informed backward pass that's maybe slightly different from the forward pass. But I think that's mostly a problem of the controls applications to deal with. I think that we cannot really expect the contact model to solve our problem there. I think we should have maybe some value model, value function there instead. We want to hear about these long-term behaviors. And contact model is just one step, right? Shouldn't expect too much from it.
And maybe a comment about the contact models. There is 2 things. There is contact modeling, what is the physical contact, and how you plug it to your ICP. So when you're on server, you also then server BI to really have the contact. For me, there is 2 sorts of noises, and currently we are always taking one contact model and one server together, which is maybe on larger scope of the potential contact models we want to capture, and also the type of servers we want to work with. And there is a lot of work and a room of contributions to do at this level. And I think we are still missing some ideas and some contribution at this level. Force to try and I think, for example, the work would be a nice template framework to try to investigate all this type of possibilities.
reality, simulate an envelope of reality. When you do that, you might not be right, but you're never going to be wrong because you have that region. And in many cases, this is more useful than try to get the finest possible simulation and getting the median right there aligned with reality. Right? So should we invest more time in making simulators more stochastic, giving you ranges instead of making them more accurate? At one point?
I can first answer yes, to answer that, but I will only answer from the learning-based dynamics perspective. So actually, neural networks is actually, there's a lot of tools of how to make neural network predict not just like one deterministic trajectory, but actually predict a distribution, or at least like represents a distributions. So actually, we are trying to like investigate something about combining, for example, diffusion with like neural dynamics model. They're trying to generate for them not just one outcome, but multiple possible outcomes. And I believe having some like a formal characteristics about the distribution, about uncertainties, about the future predictions can be very useful in practice for several reasons. One, you could understand like how uncertain you are about parameters already estimated in your models. Like, do you need to do more explorations to help you to do the estimation, or now we can just use the model to do plannings? And second, it can help you to understand like where and when to trust your model. Do you need to collect more data? And those uncertainty measurements can actually help you to understand like where to collect more data and how much more data might be useful. Like for example, you have like a budget for 1,000 more interactions. Like where should you collect that 1,000 more interactions? I think that can be very useful. Obviously, also for safe planning.
So one of the results we actually had in the generalized stochastic smoothing is that you can differentiate the output variance with regards to your input location and input variance. So I think that could be an interesting direction also to experimentally look more into, to take those uncertainties into account, not only with the input standard deviation that you may use in your simulation, but also the output standard deviation if you have a stochastic simulation.
I think this was also done with Julia, right? There's this interval arithmetic that can measure like how the input variances affect the output variances. I think they can also do this, just changing the scalar types of the simulator to infer those intervals. But on the other hand, I heard also like there's this paper from West Tedrak's group that actually showed when you have a stochastic contact model, just do multiple rollouts and then do a policy gradient with this. It's the same as having a smooth contact model, just use gradient descent with it. So I think you can sometimes overcome all this massive sampling by just having an overall smoother model. And then the effect is the same. I mean, they only showed it for ball bouncing against the wall or the ground or something, but it would be interesting to see how this translates to real robots, I assume. Yeah, and on the other hand, I think the massive parallelism affords you to do these particle-based representations, because the simulator itself is really deterministic technically. There's only uncertainty in the parameters that could explain some variance. So whether it's in the sensor model or in the physics parameters, that's the only source of error, basically, that the other equations are known, right? So maybe that's the way to see it. And then you just need to sample all these parameters on the right spaces, the right priors, and then you get these outcomes that are more close to the real world.
Yeah, unless you have stochastic behavior, like chaotic systems, like that, in which case.
But even there, it's only dependent on the initial conditions, right? And those are known. But our double pendulum moves is known. It's just not known what actually is the state you're in, what are the masses and things. So that's fine.
One last question for audience.
Maybe a quick question for you. Maybe I'm mistaken, but if you're talking about making graph neural networks as the general functional cluster to represent core models, when do you see that you can use the data you collected and build some physical connections through this work? Like,
say you have two ping pong ball and you collect a lot of data and find out the contact actually can be represented by some graph neural network. And did you see the actually it corresponds to the physics? Would you see the potential that it will correspond to the physics, or like how do you see it might in the end we get a lot of data and in the end we want to distill it to F equals MA? When do you see that point come?
Okay, so thank you for the questions. So currently, you could imagine like this type of neural dynamics model is, I would say, a type of position-based dynamics, essentially just predicting the delta positions of the movements of those particles. Like initially, we started with position-based dynamics, the NVIDIA flags, and trying to learn a model for NVIDIA flags. That's how we are getting everything started. So how to actually distill some kind of physical rule from it? There was like we have actually one project, like we are trying to do sparsifications of the neural dynamics model. So in that specific project, what we realized is that if you want to use some more principled optimization tools like mixed integer programming to do trajectory optimizations, the neural network is just so over complicated for MIP to be scalable. So what we do is trying to sparsify the neural network as much as possible to an extent where MIP becomes tractable, which was actually a paper last year at New York. So we were hoping, for example, after enough sparsifications, maybe some kind of physical rule will emerge. We didn't observe that, at least from our limited amount of studies, because our goal was still trying to use that for planning. But maybe like with some better ways and more clever ways of doing sparsification, something will emerge. But yeah, we don't know yet.
Okay, I will close with one last question, which is, let's say, look forward. So what do you think, when is the exact moment for differentiable simulation in robotics, and what field maybe first? So what I call exact moment is, for example, my background in locomotion, and recently, let's say the new paper, I would say maybe more than half they prefer to use Isaac Gym or Isaac Sim because super easy to use and already have very nice simple real pipeline. So based on your experience and also your insights, maybe when will be the such kind of Isaac moment for different simulation in robotics, and also which field maybe or which application field will be the first, let's say more and more people, their first choice will be about the simulation.
Yeah, I think once we can really easily create simulations from the real world, I think that would be really a big block in robotics to move it forward. And you can actually take the video, have a robot interact with the world, and then automatically it creates a simulator for it. So the geometry, the physical properties, and then I think this would be also really easy for people when you just automatically have this generated. And yeah, I think the algorithms themselves, they probably will follow. And I don't know if it needs to be differentiable necessarily for that, but at least to infer some parameters maybe of some unknown objects. I think there could be some benefit to it. But the main part is really authoring the scene and inferring the right parameters to make real to sim just super easy.
So Isaac Gym and Isaac Sim has been quite like useful and actually powerful in locomotion type of research. And one important lesson I actually learned from those series of papers is that your simulation doesn't have to be perfect. Like it doesn't simulate like bushes, it doesn't simulate the snow, sands, but with enough randomization in simulation, you can actually obtain a pretty good policies that work pretty robustly in the real world. But we didn't see that. We haven't seen that for manipulations. I think the main reason being that the gap between simulation and real world matters much more for manipulation than for like locomotions. So currently we have seen examples where, for example, you do like in-hand reorientations of type of projects. Those are great. Those are very impressive. But we haven't really seen a lot of like works that just do simple real transfers for interactions with more complicated like real world. So this is actually a very interesting question, is that how accurate does the simulation has to be in order for sim to real to transfers? So there's one actually interesting thing I learned from those type of like dexterous manipulations, like bimanual. There's a bunch of work like that. They do not have to instantiate the simulations exactly as the real world, but they have to instantiate the environment in a way that can encourage this type of behaviors to emerge. And it's actually human doing reinforcement learning. Human trying to tune the parameters of how to instantiate those environments, such that the trained policy in those type of environments can work robustly in the real world. These are whole long, like non-differentiable pipeline where humans are doing the reinforcement learning. That's not satisfying to me. So at a point where we can do very good sim-to-real transfer, and we really have a good understanding like how accurate simulation has to be. I think that's when we know when we have the such moments.
I don't think I have anything to add.
Okay, so since our speaker again, I'm looking forward to our